In this lecture we'll find out the length of line segment X using two different methods. In the drawing we have a semicircle inside a quarter circle. We know that side AO equals to 6 units. AC is tangent to this semicircle at this point. And we want to find out the length of side AC that is equal to X. So we'll start with the first method and we'll define the center of this semicircle as point P. We'll define the point of tendency of tangent AC with this semicircle as point D. Here, because of the fact that AOB is a quarter circle, this angle must be equal to 90 degrees, and point O is the center of the quarter circle. Point A is the point on the quarter circle itself, that is to say OA is the radius of the quarter circle that is equal to 6 units. For the same reason, exactly, OB, it is also the radius of the quarter circle, that is to say it will be equal to 6 units also. But OB, it is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter of the semicircle equals to 6 units, therefore the radius of the semicircle will be equal to 3 units. So OP, that is the radius of the quarter circle, will be equal to 3 units. PB will be also equal to 3 units. And then we will join points P and D together by a straight line. And PD is also the radius of the semicircle, that is to say it is equal to 3 units. All the three line segments PB, PD and PO exit from the center of the semicircle, that is to say from point P, and the other side is the point on the semicircle itself, and this is exactly the definition of a radius, that is to say OP, PO and PB are the radii of the semicircle that is equal to therefore they are equal to 3 units. Okay, so in the next step we'll join points A and P together by a straight line. And I will present to you a new rule that is actually rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. From a common external point to a circle are equal. I'll read rule number 1 again. according to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have here point P, here point P is an external point in relation to this circle. Why point P is an external point? Because point P is not located inside this circle nor on this circle, but it is located outside of this circle. That is to say, therefore it is defined as an external point in relation to this circle. So if from point P we draw two tangents to this circle, so here the first tangent is tangent, and the point of tendency of the first tangent with this circle, we will define it as point A, and then we will draw a second tangent to this circle, we will define the point of tendency of the second tangent with this circle as point B, and according to rule number 1, the lengths of two tangents, that is to say, the length of the first tangent is PA, and the length of the second tangent is PB. So, according to rule number 1, the lengths of two tangents from a common external point, the common external point is point P, to a circle, to points A and B are equal. That is to say, PA is equal to PB. According to rule number 1, in this drawing, PA equals to PB. So whenever you draw two tangents to a circle from a common external point of that circle, like in this drawing, then the lengths of those two tangents will be equal to each other. In this case, PA is equal to PB. Okay? So we can implement rule number 1 in our drawing. In our drawing, we have here the common external point, point A. Point A is the common external point in relation to the semicircle. It is located outside of the semicircle. Therefore, it is defined as a common external point. From the common external point, point A, we have tangent AO and we have tangent AD. And according to rule number 1, those two tangents are equal to each other in their lengths. That is to say, AO equals to AD according to rule number 1. So I write it down. AO equals to AD according to rule number 1. But AO equals to 6 units according to what is given us in the question. Here AO equals to 6 units. And from this equation, six equals to AO equals to AD, we will derive that AD is also equals to 6 units. Okay, here AD equals to 6 units. AD equals to 6 units. In the next step, we will prove that those two right triangles can go into each other according to side rule. So actually we prove that the right ring triangle AOP can go into the right ring triangle PDA according to side rule. So I'll write it down. The green right triangle AOP is congruent the green right triangle AOP congruent, this is the sign of congruent, to the green right triangle APD according to side rule. Okay, so first of all we know that AO equals to AD equals to 6 units according to rule number 1. AO equals to AD equals to 6 units according to rule number 1. In addition, AP is a common side, it belongs to both triangles, so AP equals to AP is a common side that belongs to both triangles. And finally, OP equals to PD equals to 3 units. It is the radius of the semicircle. OP equals to PD equals to 3 units. That's the radius of the semicircle. So actually prove that all the sides of the right main triangle AOP can go into all the sides of the right main triangle ADP. Therefore, those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we will derive from it that angle OAP, this angle, equals to this angle that is actually angle PAD. Again, from the fact that the two grand triangles can go into each other, we derive that angle OAP equals to angle PAD, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles will be also equal to each other. And if we define angle OAP as theta, so if this angle OAP equals to theta according to our definition, then from this equation theta equals to angle OAP equals to angle PAD, we will derive that angle PAD is also equals to theta. The angle PAD is also equals to theta. In the next step, We will join together points O and C by a straight line. And we'll focus on the right green triangle, triangle AOP. On the right green triangle, triangle AOP, we know that tangents theta equals to OP over AO. OP over AO. OP equals to 3 units. It is the radius of the semicircle. AO equals to 6 units according to what is given us in the question. So in conclusion, tangents theta equals to 3 over 6. We divide both the numerator and the denominator of this side of the equation by 3. And we get that 3 over 3 is 1. And 6 over 3 is 2. So in conclusion, we found out that tangents theta equals to 1/2. Tangents theta equals to 1/2. In the next step, I will present to you the law of cosines. I've already talked about the law of cosines in the previous lecture, so I will do it shortly. And then we will implement the law of cosines in this triangle, triangle AOC. So what is the law of cosines? The law of cosines is true in any triangle. So if we have triangle ABC, that could be any triangle. This is triangle ABC. And we know that side AB of triangle ABC equals to A unit in its length, side AC equals to B units in its length, and side BC equals to C units in its length. Then, according to the law of cosines, C squared equals to A squared plus B squared minus 2 times A times B times, here actually the angle between side AB and side AC is alpha. So it is equal to A squared plus B squared minus 2 times AB times cosine alpha. Okay. Again, according to the law of cosines, in triangle ABC, this triangle C square equals to A square plus B square minus 2 times AB times cosine alpha. Now we will implement the law of cosines in triangle AOC. So I'll copy triangle AOC in this new page and we will implement the law of cosines in this triangle AOC. What is the length of side OC, of triangle OC? O is the center of the quarter circle. C is the point on the quarter circle itself, and this is exactly the definition of a radius. So OC is the radius of the quarter circle, that is to say it is equal to 6 units. And the angle between side OA and side AC is 2 theta. And AC is the line segment that we are looking for, that is equal to x. So we will implement the law of cosines in this triangle AOC. According to the law of cosines, this will be question number 1. Here OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. So this is the implementation of the law of cosines in this triangle AOC. OC square equals to AO square plus AC square minus 2 times AO times AC times cosine 2 theta. So OC equals to 6 units, so OC square is 6 squared, that is 36. That is equal to AO square. AO is also equal to 6, so AO square will be equal to 6 squared, that is also 36. Plus AC square. AC equals to x, so AC square is x squared. Minus 2 times AO 6 and AC is x times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled. And here what is left is 0 equals to x squared minus 2 times 6 is minus 12, So this expression equals to minus 12x times cosine 2 theta. Here we will add 12x times cosine 2 theta to this equation, equation number 1. And we get that according to equation number 1, twelve x cosine 2 theta equals to x squared. Here we will divide this equation, equation number 1 by x. You should remember that x is the length for side AC, therefore it must be a positive number, it can never be equal to 0. That is the reason that it is allowable to divide the equation number 1 by x. So we divide the equation number 1 by x and we get that here x will get cancelled and we left only with 12 times cosine 2 theta that is equal to x squared over x is x. Actually, the only thing that is left to do in order to find out the value of x, the line segment that we are looking for, is to find out the value of cosine 2 theta. Okay? Actually, we have a trigonometric identity for cosine 2 theta. Here, cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. Okay? But we have already found out that tangent theta equals to 1/2. Here tangent theta equals to 1/2. Now we can substitute tangent theta in this trigonometric identity by 1/2. So we'll do it now and we'll get that cosine 2 theta equals to 1 minus tangent square theta. Tangent theta equals to 1/2. Tangent square theta will be equal to 1/2 squared over 1 plus tangent square theta equals to 1/2 squared. Okay, so here we have 1 minus 1/2 squared is 1/4 over 1 plus 1/4. So here cosine 2 theta equals to 1 minus 1/4 is 3/4 over 1 plus 1/4 is 5/4. So here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. And in conclusion, we found out that cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in equation number 1 here by 3/5. According to equation number 1, 12 times cosine 2 theta equals to x. So we substitute cosine 2 theta by 3/5 and we will get that according to equation number 1, 12 times cosine 2 theta is 3/5, so we substitute cosine 2 theta by 3/5 and it is equal to x. So according to equation number 1, we found out that 12 times 3 is 36/5 equals to x. So actually x, that is the line segment that we are looking for, equals to 7.2 units. Okay, so here line segment AC that is equal to x is equal to 7.2 units. We finished with the first method. In the next step I will present to you how to find out the length of line segment AC that is equal to x according to the second method. In the second method, we will use all the things that we already found out in the first method. Here, the center of the semicircle is at point P. The point of tendency of tangent AC if the semicircle is at point D. This angle equals to 90 degrees. OP is 3 units, it is the radius of the semicircle. PB is also 3 units, it is the radius of the semicircle. And PD is also the radius of the semicircle, that is to say it is also equals to 3 units. We will join points P, A and P together by a straight line. We have already proved in the first method that triangle AOP is congruent to triangle APD according to side rule. I'll write it down. Triangle AOP congruent to triangle APD according to side rule, and from the fact that those two triangles congruent to each other, we conclude that those two angles are equal to each other. So if one angle equals to theta, then the other angle will be also equal to theta according to what we have already done in the first method. Okay, so from here we will do something different that we didn't did in this first method. We'll extend line segment AC, and we will extend line segment OB by a straight line until they intersect with each other. And we'll define the point of intersection between the extended line segment AC and the extended line segment OB is E. So here actually we created triangle, the right triangle AOE. In the right triangle, in this right triangle AOE, AP is angle bisector. That is to say, it divides angle OAE into two equal parts, into two halves. Each half equals to theta. Okay? So we will actually, I will present to you the angle bisector theorem, and we will implement the angle bisector theorem in this right triangle AOE. Because we have the angle bisector AP, we can implement the angle bisector theorem in this right triangle AOE. So what is angle bisector theorem? Here, angle bisector theorem. So if we have triangle ABC, that could be any triangle, this is triangle ABC. And we have the angle bisector AD. Here AD is angle bisector because of the fact that it bisects angle BAC into two halves. The first half is theta, and the second half is also theta. So, according to angle bisector theorem, we will get that the angle bisector in this triangle ABC, that could be any triangle, the angle bisector in our case, in this domain, the angle bisector is AD. So I write it down. In the triangle, in triangle ABC, in this case it's triangle ABC, divides the side that it is, again, the angle bisector AD is side BC, and it divides it into two parts. The first part is BD, and the second part is DC. So the angle bisector AD in the triangle divides the side that it is. That is to say, side BC in this case, in a ratio as I already said, angle bisector AD divides side BC into two parts. The first part is BD and the second part is DC, and the ratio between those two parts is BD over DC. In a ratio that is equal to the ratio of the angle's legs. And we are relating to the angle that has been bisected by the angle bisector AD into two halves. That is to say, we are relating to angle BAC. The legs of angle BAC are, angle BAC has two legs. The first leg is leg AB and the second leg is leg AC. And the ratio between those two legs is AB over AC. In conclusion, we actually found out that AB over AC equals to BD over DC. Okay? I'll repeat again, the angle bisector AD in this triangle ABC divides the side that it is, angle bisector AD is side BC, and divides it into two parts. The first part is BD, the second part is DC, and the ratio between those two parts is BD over DC, and that ratio is equal to the ratio of the angle's legs. We are relating to the angle that has been bisected into two halves, that is to say, angle BAC. And the two legs of angle BAC are BA and AC. And the ratio between those two legs is AB over AC. So AB over AC equals to BD over DC. That is the ratio that angle bisector AD divides side BC. In conclusion, we found out that AB, according to angle bisector theorem in triangle ABC, AB over AC equals to BD over DC. So we can implement the angle bisector theorem in our triangle, in the right triangle, triangle AOE. Okay, so I'll copy the right triangle AOE in a new page, and we will implement the angle bisector theorem in this triangle, triangle AOE. The right triangle, triangle AOE. So this is the right triangle AOE that I copied from the original drawing. AP is the angle bisector. So here, according to angle bisector theorem, the angle bisector AP divides side OE in a ratio that is equal. Angle bisector AP divides side OE into two parts, OP and PE. And the ratio between those two parts is OP over PE, and that ratio equals to, according to angle bisector theorem, that ratio equals to the ratio between the angle's legs. We are talking about the angle that has been bisected into two halves, that is angle OAE. Angle OAE. Angle OAE has two legs. The first leg is OA and the second leg is OAE. And the ratio between those two legs is AO over AE. In conclusion, according to angle bisector theorem, we get that AO over AE equals to OP over PE. Okay? AO equals to 6 units. AE is AE, and OP equals to 3 units. It is the radius of the semicircle. Here OP equals to 3 units. This is the radius of the semicircle over PE. PE is PE. Here we will divide this equation by 3, and we will multiply it also by AE, and we will get that according to equation number 1, six over 3 equals to AE over PE. Here we will multiply this equation number 1 by PE, and we'll get that according to equation number 1, 6 over 3 is 2, so it is 2 times PE equals to AE. AE equals to 2 times PE, according to equation number 1. Here we will define PE as A. PE equals to A according to our definition. Here PE equals to A, and here also PE equals to A according to our definition. So according to equation number 1, AE equals to 2PE, but PE equals to A, that is to say A equals to 2A. According to equation number 1, AE equals to 2A. AE equals to 2A. Here AE equals to 2A. In the next step we will continue to focus on the right triangle AOE, and we will implement the Pythagoras theorem on the right triangle AOE. So I'll copy the right triangle AOE in a new page, and we will implement the Pythagoras theorem on the right triangle AOE. Okay? We have already found out that A equals to 2A. So we can write here that A equals to 2A. OE, from the drawing here, you can see that OE equals to 3 plus A. Here also you can see that OE equals to 3 plus A. So you can write here that OE equals to 3 plus A. So we implement the Pythagoras theorem on the right triangle, triangle AOE. On the right triangle, triangle AOE, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This will be equation number 2. The square of the hypotenuse is AE squared. It must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to AO squared plus OE squared. Here A is 2A, so A squared is 2A squared. And it is equal to AO squared. AO equals to 6, so AO squared is 6 squared, that is 36, plus OE squared. OE equals to 3 plus A, so OE squared is 3 plus A squared. Here we will open the brackets on both sides of equation number 2, and we get that according to equation number 2, 2A squared is 4A squared, and it is equal to 36 plus 3 plus A squared. 3 plus A squared is 3 squared, that is 9, plus A squared, plus 6A. So according to equation number 2, 4A squared equals to 36 plus 9 is 45, plus A squared plus 6A. Here we will subtract from this equation, equation number 2, A squared, and we get that according to equation number 2, 4A squared minus A squared is 3A squared. That is equal to 45 plus 6A. Here we divide this equation number 2 by 3, and we get that according to equation number 2, A squared equals to 45 over 3, 3A squared over 3 is A squared, and 45 over 3 is 15, plus 6A over 3 is 2A. So here we subtract 2A and also 15 from this equation, equation number 2, and we get that according to equation number 2, A squared minus 2A minus 15 equals to 0. So we have here a quadratic equation, and the coefficient A in this quadratic equation equals to 1. The coefficient B equals to minus 2. and the coefficient c equals to minus 15, and the variable that we're looking for in this quadratic equation is a, so x equals to a. And the general solution, the general formula for solution of a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Okay, so we'll put the data inside the formula and we'll find out the value of the values of a, because here x equals to a. So here a equals to minus b, b equals to minus 2, so minus b is minus 2, that is 2, plus minus square root of b squared, b equals to minus 2, so minus b squared is minus 2 squared, that is 4, minus 4 times a is 1, times c, that is minus 15, over 2a, a is 1, so 2a is 2 times 1, that is 2. So here we have a equals to 2 plus minus 4 times minus 15 is 60, and 60 plus 4 is 64. So inside the root what is left is only 64 over 2. So here a equals to 2 plus minus the square root of 64 is 8 over 2. So here we will have two solutions that are possible for a. The first solution is a equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that a equals to minus 3. But because of the fact that a is the length of side PE, it must be a positive number. So a is a length therefore it must be a positive number. So we cancel this solution because a must be a positive number as a length, and we're left only with the second solution. That a equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So a equals to 5 units. We found out that a equals to 5 units. Therefore 2a is 2 times 5, that is 10. That is to say AE equals to 10 units and A equals to 5 units. In the next step we will find out the length of line segment BE. Here from the drawing it is very easy to see that the length of line segment BE it is equal to PE minus PB. PE minus PB. Okay, BE equals to PE minus PB. So here BE equals to PE equals to A, that is equal to 5 units, minus PB equals to 3 units, it is the radius of the semicircle, so in conclusion, we found out that B equals to 5 minus 3, that is 2. So BE equals to 2 units. Can I tell down that BE equals to 2 units? In the next step, we will find out the value of line segment CE. Here, CE, for the drawing, it is very easy to see that CE, the length of line segment CE equals to AE minus AC. Again, CE equals to AE minus AC. I'll repeat again. CE equals to AE minus AC. So CE equals to AE, that is 10 units, minus AC, that is equal to X according to what is given us the question. So, in conclusion, we found out that CE equals to 10 minus X. So can I tell that CE equals to 10 minus X. Okay, so in the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and then we will extend line segment BO by straight line until it intersects with the circle at this point. We define the touching point of the extended BO and the circle as point M. So what is the length of line segment MO? Line segment MO starts from point O, that is the center of the circle and also the center of the quarter circle, and ends at point M, that is a point of the circle itself. And this is exactly the definition of a radius, that is to say, MO is the radius of the quarter circle, that is also equal to the radius of the circle itself, that is to say, it is equal to 6 units. Okay? So in the next step, I will present to you a new rule, that is actually rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, in our case the intersection point will be point P. Then the following equation is true. So read rule number 3 again. If two chords intersect with each other outside the circle at point P, then the following equation is true. So we have two chords. First of all, we have the external point P that is outside the circle, and point P is the external and the intersection point. So we have here the first chord. This is actually chord AB that intersects with chord CD. This chord at point P. Point P is the intersection point. Intersection point of the two chords called AB and called CD. And point P is located outside the circle. Therefore, the following equation is true, that PA times PB is equal to PC times PD. I repeat again, chord AB intersects with chord CD at point P. Point P is the intersection point of the two chords, and point P is located outside the circle. So in this case, the following formula is true, that PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. We can actually implement rule number 3 in our drawing. Why? Because in our drawing we have chord AC intersects with chord MB, at point E. Point E is the intersection point of chord. Point E is the intersection point of chord AC with chord MB. I repeat again. In our drawing, chord AC intersects with chord MB at point E. Point E is the intersection point of chord AC with chord MB. Therefore, according to rule number 3, we will get that EC times EA, EC times EA, EC times EA equals to EB times EM. I repeat again. Because of the fact that chord AC intersects with chord MB at point C, then according to rule number 3, the following equation is true that EC times EA equals to EB times EM. Okay? EC equals to x 10 minus x, EA equals to 10 units, and it is equal to EB equals to 2 units, times EM, line segment EM equals to 6 plus 3 plus 3, that is 12, plus 2, that is 14. So in conclusion, we found out that according to this equation, 10 minus x times 10 equals to 2 times 14. 2 times 14 is 28, and it is equal to 10 times 10 minus x. Here we divide this equation by 10, and we get that 10 minus x equals to 28 over 10 is 2.8. 2.8. Here we will add to this equation x, and we will subtract 2.8, and we will get that x equals to 10 minus 2.8, that is 7.2 units. So we actually found out that x equals to 7.2 units. In both methods, we arrive to the same result, that the length of line segment X, it is equal to 7.2 units. Okay? Here, line segment AC, it is equal to X, it is equal to 7.2 units. In the next step, I will summarize the lecture. We will start with the first method. So I repeat on the question, we have here a semicircle inside a quarter circle. We know that side AO equals to 6 units. Side AC is tangent to this semicircle at this point. And we want to find out the length of line segment AC that is equal to X. So we define the center of the semicircle as point P. The point of tendency of tangent AC with this semicircle as point D. And here, because of the fact that this is a semicircle, this is a quarter circle, AOB is a quarter circle, this angle must be equal to 90 degrees. And AO must be equal to the radius of the quarter circle. For the same reason, OB must be also the radius of the quarter circle because of the fact that it starts from the center of the quarter circle, that is to say from point O, and then at point B, that is the point of the quarter circle itself. So therefore OB equals to 6 units, this is the radius of the quarter circle. But OB is not only the radius of the quarter circle, but is also the diameter of the semicircle itself. So we know that the diameter of the semicircle equals to 6 units, therefore the radius will be half of it, that is to say it will be equal to 3 units. So OP equals to PB equals to PD, that is 3 units. All the line segments are defined as the radii of the semicircle because of the fact that they start from the center of the semicircle and ends at any point on the semicircle itself. And this is exactly the definition of a radius. So all the line segments are the radii of the semicircle that is equal to 3 units. Okay. Then we join points A and P together by a straight line. And then I presented to you a new rule that is actually rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So here we have this circle, and from the common external point P, we drew two tangents to this circle. The first tangent is tangent PA, and the second tangent is tangent PB. And according to rule number 1, the lengths of two tangents will be equal to each other. That is to say, PA equals to PB. So whenever you draw two tangents to a circle from a common external point through that circle, then the lengths of those two tangents will be equal to each other. In this case, PA will be equal to PB. You can implement rule number 1 in our drawing, because in our drawing we have the common external point A, and from the common external point A we have two tangents to this semicircle. The first tangent is tangent AO, and the second tangent is tangent AD. And according to rule number 1, whenever you have two tangents that exist from a common external point to the circle, then the lengths of those two tangents will be equal to each other. In this case, AO must be equal to AD according to rule number 1. Here AO equals to AD according to rule number 1, but AO equals to 6 units according to what is given as the question. Here AO equals to 6, so from this equation 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. Here AD is also equals to 6 units. In the next step, we proved that the two green right triangles can go into each other according to side rule. So why those two triangles can go into each other? First of all, AO equals to AD equals to 6 units. We just right now found out that AO equals to AD equals to 6 units. AP is a common side that belongs to both triangles. So AP equals to itself, and OP equals to PD equals to 3 units. So all the sides of triangle ADP can go into all the sides of triangle AOP. Therefore, those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we will derive that those two angles are equal to each other. We will derive that angle PDAP equals to angle PAD according to the rule that corresponding angles in congruent triangles are equal to each other. And if angle DAP equals to theta, then from this equation, theta equals to angle DAP equals to angle PAD, we derive that angle PAD is also equal to theta. Okay, so both those two angles are equal to theta. Then we focus on the right triangle AOP. In the right triangle AOP, triangle theta equals to OP over AO. Triangle theta equals to OP over AO. OP is the radius of the semicircle, that is to say it is equal to 3 units, and AO equals to 6 units is given us in the question. So in conclusion, triangle theta equals to 3 over 6. We divided both the numerator and the denominator of this side of the equation by 3, and we got that 3 over 3 is 1 and 6 over 2 is 3. So in conclusion, we found out that triangle theta equals to 1 half. Here, triangle theta equals to 1 half. Then we connected together points O and C together. We connected together points O and C. And I presented to you, so we created triangle AOC, and then I presented to you the law of cosines, and we implemented the law of cosines in this triangle AOC. So what is the law of cosines? The law of cosines is true in any triangle. So if you have this triangle ABC, that could be any triangle. Side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length, and the angle between side AB and side AC is alpha. Then, according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. Okay, then we implemented the law of cosines in triangle AOC. I copied triangle AOC in the original drawing. Here angle OAC equals to theta, AC equals to x. This is the line segment that we are looking for. AO equals to 6 units according to what is given as the question. And here OC, line segment OC, exists from point O, that is the center of the quarter circle, and C is the point of the quarter circle itself. And this is exactly the definition of a radius. That is to say, OC is the radius of the quarter circle, that is to say it is equal to 6 units. Then we implemented the law of cosines in this triangle AOC. According to the law of cosines, we will get that OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. Okay? OC equals to 6, OC squared is 6 squared, that is 36. OA is also equals to 6, therefore O squared is 6 squared, that is also 36. Plus AC squared, AC is x, so AC squared is x squared, minus 2 times AO, that is 6, times AC, that is x, times cosine 2 theta. Here we have 36 on both sides of the equation, so 36 will get cancelled. And what is left after we cancel 36 from equation number 1? In this side we have 0, on the other side we have x squared, and minus 2 times 6 is minus 12, so this expression equals to minus 12x times cosine 2 theta. Here we added 12x cosine 2 theta to this equation, equation number 1, and we got that according to equation number 1, 12x cosine 2 theta equals to x squared. We divided this equation, equation number 1 by x, And we got that here x will get cancelled and we left only with 12 cosine 2 theta that is equal to x squared over x is x. So in conclusion, we found out that according to equation number 1, 12 times cosine 2 theta equals to x. So the only thing that is left to do in order to find out the value of x is to find out the value of cosine 2 theta. We have trigonometric identity for cosine 2 theta. According to this trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. And we have already found out that tangent theta equals to 1 half, so we can substitute tangent theta in this trigonometric identity by 1 half. We did it and we got that cosine 2 theta equals to 1 minus tangent square theta. Tangent theta equals to 1 half. Therefore, tangent square theta will be equal to 1 half squared over 1 plus tangent square theta that is equal to 1 half squared. So here we have cosine 2 theta equals to 1 minus half squared. Half squared is 1 quarter. So here we got that cosine 2 theta equals to 1 minus 1 quarter over 1 plus 1 quarter. 1 minus 1 quarter is 3 quarters, and 1 plus 1 quarter is 5 quarters. So in conclusion, we got that cosine 2 theta equals to 3 quarters over 5 quarters. Here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. And we left only with cosine 2 theta that is equal to 3 fifths. Cosine 2 theta equals to 3 fifths. Now we can substitute cosine 2 theta in equation number 1 here by 3 fifths. We did it and we got here equation number 1, according to equation number 1, 12 times cosine 2 theta equals to x. So we substituted cosine 2 theta by 3 fifths and we got that 12 times cosine 2 theta is 3 fifths, that is equal to x. 12 times 3 is 36 and 36 over 5 is 7.2. So in conclusion, we found out that the length of line segment x that is equal to AC is equal to 7.2 units. We finished with the first method. In the next step, I will present to you how we found out the value of x according to the second method. Okay, in the second method, we relied on the things that we have already found in the first method. Here OP equals to 3 units, PB equals to 3 units, PD also equals to 3 units. This again equals 20 degrees. And OB is the radius of the quarter circle that is equal to 6 units. And actually we already found out that those two right triangles can go into each other according to side rule. And from that fact we derived that those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle equals to theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Okay? So both those two angles are equal to theta. Then we extended line segment AC and line segment OB by straight line until they intersect with each other at point E. In this way, we created the right triangle AOE. In the right triangle AOE, we have the angle bisector AP. So we can implement the angle bisector theorem in the right triangle AOE. So first of all, I presented to you the angle bisector theorem. So, what is the angle bisector theorem? The angle bisector theorem states that the angle bisector AD is the angle bisector because of the fact that it divides angle BAC into two halves. Each half equals to theta. So the angle bisector AD in triangle ABC, that could be any triangle, divides the side that it eats. Angle bisector AD eats side BC and divides it into two parts. The first part is BD and the second part is DC. And the ratio between those two parts is BD over DC. And that ratio equals to the ratio of the angle's legs. We are talking about the angle that has been bisected by angle bisector AD. That is to say, we are talking about angle BAC. Angle BAC has two legs. The first leg is leg AB and the second leg is leg AC. And the ratio between those two legs is AB over AC. That is to say, the ratio between those two legs, that is AB over AC, equals to the ratio that angle bisector AD divides side BC. And the ratio that angle bisector AD divides side BC is BD over DC. That is to say, in conclusion, AB over AC equals to BD over DC. Okay, so here we implemented the angle bisector theorem in our triangle AOE. This is a right triangle. In triangle AOE, we have the angle bisector AP that divides angle OAE into two halves. Each half equals to theta. So AP is the angle bisector in triangle AOE. And according to angle bisector theorem, the ratio that the angle bisector AP divides side OE is actually OP over PE. And that ratio equals to the ratio between the angle's legs. We are talking about the angle that has been bisected, that is angle OAE. The legs of the angle that has been bisected is OA and AE. Those are the two legs of the angle that is bisected, and the ratio between those two legs is OA over AE. So the ratio between the two legs of the angle that is been bisected is OA over AE, and it is equal to the ratio that angle bisector AP divides side OE. The ratio that angle bisector AP divides side OE equals to OP over PE, and it is equal to the ratio between the angle's legs, that is OA over AE. So AO over AE equals to OP over PE. Okay? AO equals to 6 over AE, and OP equals to 3 units. This is the radius of the semicircle over PE. We divided equation number 1 by 3, and then we multiplied by AE, and we found out that 6 over 3 equals to AE over PE. 6 over 3 is 2. Then we multiplied the equation number 1 by PE, and we got that 2 times PE equals to AE. We defined PE as A. Here PA equals to A according to our definition, and here also PE, line segment PE equals to A according to our definition. And so according to equation number 1, 2 times PE equals to AE. But PE equals to A according to our definition. Therefore, according to equation number 1, 2 times PE is 2A, that is equal to AE. So we found out that AE equals to 2A, and according to our definition, PE equals to A. So we continue to focus on the right triangle AOE, and we implemented the Pythagoras theorem on the right triangle AOE. So I copied the right triangle AOE in this new page. We have already found out that A equals to 2A, AO equals to 6 units according to what is given as the question, and what is the value of OE. Here you can see here that OE equals to 3 plus A. Okay, here O equals to 3 plus A. We implemented the Pythagoras theorem on the right triangle, triangle AOE. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say the square of the hypotenuse is AE square, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to AO square plus OE square. So A equals to 2A, so A squared is 2A squared, and it is equal to AO squared. AO is 6, so AO squared is 6 squared, that is 36, plus OE squared. O equals to 3 plus A, so OE squared will be equal to 3 plus A squared. So we open the brackets in both sides of this equation number 2, and found out that 2A squared is 4A squared, equals to 36, plus 3 plus A squared equals to 3 squared, that is 9, plus A squared plus 6A. In conclusion, we found out that 4A squared equals to 36, plus 9 plus A squared plus 6A. 36 plus 9 is 45. So in conclusion, we found out that 4A squared equals to 45 plus A squared plus 6A. We subtracted A squared from this equation number 2. And here 4A squared minus A squared is 3A squared equals to 45. A squared minus A squared is 0 plus 6A. We divided this equation number 2 by 3, and we got that 3A squared over 3 is A squared, 45 over 3 is 15, and 6A over 3 is 2A. In conclusion, we found out that according to equation number 2, A squared equals to 15 plus 2A. We subtracted 15 and also 2A from this equation number 2, and found out that according to equation number 2, A squared minus 2A minus 15 equals to 0. So we have here a quadratic equation, and the coefficient of this quadratic equation is the coefficient A equals to 1, the coefficient B equals to minus 2, and the coefficient C equals to minus 15. Okay? And the variable that we are looking for in our quadratic equation is A. And the general formula for a solution of a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times AC over 2A. So here we put the data inside the formula in order to find out the value of the values of A, because in our case x equals to A. So A equals to minus B, B equals to minus 2, so minus B is minus 2, that is plus 2. And plus minus square root of B squared. B is minus 2, so B squared is minus 2 squared, that is 4. Minus 4 times A is 1, times C is minus 15. Over 2A, A is 1, so 2 times 1 is 2. So here we found out that A equals to 2 plus minus. Here we have minus 4 times minus 14, that is plus 60. 60 plus 4 is 64. So inside the root, what is left is only 64 over 2. So here we have A equals to 2 plus minus, the square root of 64 is 8 over 2. So here we have two solutions that are possible for A. The first solution for A is A equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that A equals to minus 3. But here A is the length of side PE. So A as a length must be a positive number. It can never be equal to minus 3, that is a negative number. So we cancel this solution, and we left only with the second solution, that A equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that A equals to 5 units. Therefore 2A is 2 times 5, that is 10. So A equals to 10 units. P equals to 5 units. Then we found out the length of line segment BE. Here BE, from the drawing it is very easy to see that BE equals to PE minus PB. Again, BE equals to PE minus PB. Okay? Here BE equals to PE minus PB. So B equals to PE. PE equals to A, that is 5 units. So P equals to 5 units. minus PB. PB equals to 3 units. It is the radius of the semicircle. So in conclusion, B equals to 5 minus 3, that is 2. B equals to 2 units. And then we found out the length of line segment CE. From the drawing, it is very easy to see that the length of line segment CE, it is actually equals to AE minus AC. Again, AE minus AC equals to CE. Okay, CE equals to AE minus AC. AE equals to 10 units. AC equals to X. That is the line segment that we are looking for in this question. So in conclusion, we found out that CE equals to 10 minus X. Here, CE equals to 10 minus X. In the next step, we completed the quarter circle to a circle, and we extended line segment BO by a straight line until it touches the circle at point M. Point M is the touching point of the extended line segment BO and the circle. What is MO? MO is the radius of the quarter circle because of the fact that it starts from the center of the quarter circle, that is also the center of the circle itself, and ends at point M, that is a point on the circle itself. And this is exactly the definition of the radius. So OM is the radius of the circle, that is also equal to the radius of the quarter circle, that is equal to 6 units. Then I presented to you a new rule that is actually rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true. So here we have chord AB that intersects with chord CD at point P. Point P is the intersection point of chord AB with chord CD. As you can see, point B is outside the circle, so the intersection point of the two chords is happening outside the circle. So if this is the situation, then the following formula is true, that PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. So we can actually implement rule number 3 in our drawing, because in our drawing we have chord AC that intersects with chord MB at point E. Point E is the intersection point of chord AC with chord MB. That is, the intersection point is happening outside the circle, that is point E is outside the circle. Therefore, so I repeat again, chord AC intersects with chord MB at point E. Point E is the intersection point of the chord AC with chord MB. Therefore, according to rule number 3, we will get that EC times EA equals to EB times EM. Okay, again, EC times EA equals to EB times EM. Again, EC times EA equals to EB times EM, according to rule number 3. EC equals to 10 minus X. EA equals to 10. EB equals to 2. And EM equals to 6 plus 3 plus 3, that is 12, plus 2, that is 14. So in conclusion, ME equals to 14 units. ME equals to 14 units, or EM is the same. So 10 minus X times 10 equals to 2 times 14. 2 times 14 is 28. So in conclusion, we found out that 10 times 10 minus X equals to 28. We divided this equation by 10, and we got that 10 minus X equals to 28 over 10 is 2.8. Here we added to this equation X, and we also subtracted 2.8, and we found out that X equals to 10 minus 2.8. 10 minus 2.8 is 7.2 units. So in conclusion, we found out that X, line segment AC, that is equal to X, it is equal to 7.2 in both methods. Okay, so the answer to the question that line segment AC that is equal to x, it is equal to 7.2, and we arrived to the same answer in both methods. Okay, thank you very much.